In this video, you're going to learn about seismic attenuation and automated gain control or AGC. Previously, you learned that using reflection seismology, we can obtain a detailed image of subsurface through which we can identify different geological structures. And this is so critical for oil and gas exploration. And in order to obtain such a detailed image of subsurface, we have to apply several processing steps. And in this course, I'm going to cover 8 basic processing steps. However, in practice, there are more processing that we have to apply to seismic data in order to get a more accurate image of subsurface. But it is something basic, and if you are given seismic data, by applying these processing steps, you can get some image of subsurface. So as you see here, the first step that we may apply to the seismic data is automated gain control or AGC. So why this step is important? Because the seismic wave, once the seismic wave propagates through the earth, it undergoes attenuation. And in order to address the attenuation, so we have to apply AGC. So just let's go step by step to see what AGC is. Before that, we have to learn about seismic attenuation. Assume that here we have a very simple geological model composed of 3 layers and 2 interfaces. So as you see, if we place the source and receiver in these 2 locations, so we're going to have 2 reflections, one of them from the boundary between the first and the second layer, and another reflection from the boundary of the second and the third layer. If you look at this equation shows the travel time for the first reflection event, and the second equation shows the travel time for the second reflection event. And so as a result, we're going to have to, if we look at the seismic data, we're going to see 2 hyperbolic events. And so the hyperbolic events that comes from the shallow reflector appears in the beginning of the seismic section, and what you see here for the second reflector appears at the later time. And this is something that can be verified by comparing these 2 equations. So in other words, if we look at a seismic shot record, we're going to see several reflection events, as I mentioned before. So what we see in the beginning can be linked to shallower reflectors, and what we see at the end of seismic record can be linked to deeper reflectors. So this is how we can interpret different reflection events that we see on a seismic shot record. So having said that, now I can explain the concept of seismic attenuation better. So what you see here in figure A, we see a raw seismic shot record. So if we go to the field and if we collect some seismic data, if we look at seismic shot record, if we don't apply any processing to our seismic data, this is something that we should expect to see. And as you see, almost after 2 seconds, we see no significant seismic energy or seismic event. And in figure B is the same shot record, but after applying a processing step that is called automated gain control or AGC. So as you see here, after applying AGC, we can see seismic energy even at the end of the seismic shot record. So it means that we have been able to amplify somehow the energy of low energy events. So here is the question. Just let's look at figure A. Why are not deeper reflectors observable in figure A? So the reason, because the seismic attenuation. So in other words, once the seismic wave propagates through the earth, it undergoes attenuation, And that's the reason the seismic energy becomes weaker and weaker. And when we look at deeper reflector, almost we see no energy. There are several mechanisms to explain the seismic attenuation. However, in this course, I'm going to explain two of them that are more important. So one of them is geometrical spreading, one of the mechanisms that contribute to attenuation, and the second one is intrinsic absorption. So what is geometrical spreading? So we know that, for example, if we think about body waves, the body wave propagates through the earth in the form of a sphere, or in other words, their wavefront is spherical. And another principle that we believe is the conservation energy. So we know that once the seismic wave propagates through the earth, the energy shouldn't increase if there is no any other attenuation mechanism. So in other words, if we integrate the seismic energy over the time, so we should always get the same energy. I'm talking most about kinetic energy. So having said that, so once the seismic wave propagates through the sphere, in order to meet the principle of the conservation energy, so over the sphere area, the integration of the energy should be the same. So as a result, this is very important concept. The energy per area of the seismic wave decreases as the seismic wave propagates through the earth. And because body waves propagate spherically, the energy loss due to the geometrical spreading is proportional to 1 over r squared. Okay, so just notice. So we have assumed, so again, just let me explain it again. So we have the energy, and that energy propagates through the earth. So the most important concept here is the energy per area. So in other words, if we assume like one sphere here, and if we consider a small element of the sphere, so energy per area for that small energy is proportional to 1 over r squared. So in other words, once the seismic wave propagates through the earth, energy per area decreases. And it is very interesting that the seismic amplitude is proportional to the square root of energy. So in other words, because the energy decreases 1 over r squared, so we should expect that the seismic amplitude decreases in order of 1 over r. And this is something that we can call it geometrical spreading. Unlike body waves, surface waves such as ground rolls propagate cylindrically. So we should expect that their energy per area decreases proportional to 1 over r. And as a result, because A, or the amplitude of the seismic signal, is proportional to the square root of E, or the energy, so for surface waves, the amplitude decreases 1 over the square root of r, and r is the distance from the source. Doesn't matter if we deal with body waves or surface waves, we should expect some attenuation due to geometrical spreading, but because of the nature of body waves and how they propagate, they are attenuated faster due to the geometrical spreading. Another mechanism that contributes to attenuation is intrinsic absorption. So what is that? The Earth is not 100% elastic, and it has some viscoelastic property. So it means that once the seismic wave propagates through the Earth, a fraction of its energy is converted to heat. So in other words, assume that for example, in the case of planar wave, that we have no geometrical spreading. If we have the seismic wave that propagates through some, for example, area, this is E1, this is E2. Once the seismic wave passes through that area, a fraction of that energy is converted to heat. So as a result, we can define one important parameter that is called quality factor. So assume that E is the initial seismic energy and delta E is the energy loss. So if just assume that in such a condition that there is no energy loss, or in other words, assume that we have a perfect elastic medium, so delta E would be equal to 0, so the quality factor will be very high. On the other hand, whenever we are in a very attenuating medium with a lot of viscoelastic property, in such a case, the energy is converted to heat and the quality factor decreases. So quality factor is a property to somehow quantify intrinsic absorption. Higher quality factor means lower attenuation due to the intrinsic absorption, and a smaller quality factor means higher attenuation. This table shows the quality factor for both P waves and S waves for different rocks. For example, compare shale with sandstone granite. It is something that is interesting is that, for example, shale has lower quality factor compared to sandstone. It means that the attenuation in shale is higher. And for example, if we compare granite even to sandstone, granite has much higher quality factor. So it means that granite has better elastic property compared to sandstone. Something that is interesting here, for example, outer core, as you see, for example, the quality factor for S-wave is 0. And doesn't matter what type of rock we are dealing with, always the quality factor of the S-wave is lower than P-wave. So it means that the S-waves in general are attenuated in higher rates in the nature. So maybe that's the reason, one of the reasons why in reflection seismology we usually prefer to use P-wave in order to image subsurface. So just let me ask you one interesting question, and that is, why is the outer core, the quality factor of outer core is 0? So we know that the outer core is liquid and the S-wave cannot propagate through the liquid, and so that is the reason for outer core quality factor is 0. So as I mentioned before, so when we talk about the attenuation due to the intrinsic absorption, it is proportional to 1 over Q. So the lower Q, higher attenuation. And in general, what we can do here, we can write down the equation for the intrinsic absorption in this form. Here, F is the frequency of the signal, T is the time, and Q is the quality factor. Or we may write down this equation in terms of alpha, that is attenuation. So as you see here, this equation shows once the seismic wave propagates in time, its amplitude decreases due to the intrinsic absorption. So here we can do something. Assume that here we have F, and F is the frequency, as I mentioned before, and here lambda is the wavelength. And we know that in general, frequency is equal to V, or the velocity, over lambda. So just if in this equation we insert V over lambda, then we're going to end up this equation. So the reason, because if just assume that here instead of F, I insert V over lambda, and this is the interesting that something that I'm going to have here, and V times T, velocity times velocity times time, is equal to the distance, or R. So this equation can be written also in terms of R, and R is the distance from the source. So here, just let me give you some interesting observation. As you see, if we look at this equation shows that when we talk about intrinsic absorption, the frequency matters. And in order to better explain this situation, consider that for a medium, alpha is equal to 0.1, or the quality factor is 10. And now I assume two different signals. So one of them with the frequency of 1 Hertz and another with the frequency of 5 Hertz. If you look at this figure, something that you can easily notice, you're going to notice that the signal with higher frequency is attenuated faster. And this is something that happens in the nature. Even for the same attenuation, say 0.1, 0.2, whatsoever it is, the signals with higher frequencies are attenuated faster compared to lower frequencies. So now just let me ask you another question. Assume that we want to study a formation that is very deep. What source should we use? A source that generates low frequency seismic signal or high frequency? So a source that generates low frequency is more appealing, and the reason because higher frequencies are attenuated faster, so that's the reason we may not be able to study the target if we use a high frequency source. So if I just want to combine the two attenuation, one of them is geometrical spreading and another is intrinsic absorption. This is the equation that considers both attenuation mechanisms for the seismic energy. So here we may notice that due to these two important factors, the seismic energy significantly is attenuated as it propagates through the earth. Okay, so what we should do, we should apply some processing in order to amplify the energy of low amplitude events. And this is the reason why we may apply AGC. So AGC is very easy method that we may apply to our seismic data in order to amplify the energy of low amplitude events. So in other words, we have to apply AGC if we want to see energy of the seismic signal within this area or within this seismic section that we almost see no seismic event. So how does AGC work? AGC indeed is a window that we consider. So in other words, the length of the window depends on us. We may consider to be, say, 200 milliseconds or 500 milliseconds. That is up to us. And we may find an optimum window length by trial and error. I'm going to talk about it, why, what we should consider later, but just let me explain the concept first. So assume that here we consider a window with a specific length, say 200 milliseconds. And in the center of the window is located at Ti. So what we can do, we can read the seismic amplitude at the time Ti. And now the idea is how we can calculate an amplifying factor in order to increase the seismic amplitude here. So what we do here, we read the amplitude of the seismic data that falls within this window. For example, what you see here that is indicated by red is the seismic amplitude at the time Ti, and then the rest is the seismic amplitude that we read from the seismic data that falls within this window. The next step in order to calculate an amplifying factor is, for example, to calculate the standard deviation. So if we calculate the standard deviation of these amplitudes, we're going to end up some number like that. Here, the seismic amplitudes within this window are generally low, and as a result, their standard deviation is a small number. So if, for example, we calculate the reciprocal of the standard deviation, or 1 over st, then we're going to end up a big number. And that big number can be considered as an amplifying factor. For example, here the reciprocal of the standard deviation is 3.8, and we may consider this 3.8 as amplifying factor. So if we multiply this value to the seismic amplitude at Ti, that is equal to minus 0.3034, then we can increase the amplitude or amplify the amplitude to minus 1.15. So this is how we may amplify the amplitude of low energy event by using this procedure. So as you see, the automated gain control is based on a window that we consider, and that window moves along the seismic trace, scans the entire trace, and at different times it calculates different amplifying factor, and those amplifying factors are multiplied by the seismic amplitudes that are located in the center of that moving window. So this is how we are able to somehow amplify the amplitude of low energy events. So just let me explain it here. Now consider the window at two different times. So one of them as T1 and another at T2. So at T1, as you see, the energy of the seismic data is very high. So as a result, we should expect the standard deviation should be a big number. So the reciprocal of the standard deviation should be a small number. On the other hand, at T2, because the seismic energy is very low, the amplitude of seismic energy is small. So their standard deviation is a small number, and the reciprocal of it is going to be a big number. So in other words, AGC tends to amplify the amplitude of low energy event, not high energy event. And this is something that makes it very interesting in order to increase amplification. Now just let's have some discussions about AGC. The smaller window that we choose, we can more significantly increase the amplitude of seismic data, but at the same time, we may produce some artifact. In other words, if we have some noise in our data, the amplitude of those noise also will significantly increase. This is something that we don't want to observe on our seismic data. On the other hand, if we choose very long window length for AGC, so it is possible that we are not able to somehow amplify the low energy event optimally. However, the more important thing that you should notice is that AGC is just for the display purpose. Okay, it doesn't have any physical meaning. In other words, one of the most important things that we should do in seismic data processing is to preserve the amplitude information, because the amplitude is a very important parameter, in particular in seismic data interpretation. For example, when we want to identify some important attributes such as bright spot, dim spot, and AVO, and for that reason we have to preserve the information about the seismic amplitude. So something that we should do in practice in order to have a better amplification of seismic data, we should we should calculate the energy loss due to the intrinsic absorption and also geometrical spreading. And based on these two parameters, we should calculate an amplification factor. So just have in your mind that AGC is just for the displaying purpose. It doesn't have any specific physical meaning, and in practice we should use more sophisticated processing tools in order to somehow address the problem of attenuation. Okay, just please keep in your mind that more advanced techniques are available, and in practice we should apply those techniques. So as you see here, after applying AGC, so A is the raw seismic record and B after applying AGC. Now we can see deeper reflectors better, and now we can somehow process this seismic data better. I hope that you have enjoyed this lecture and you have learned something about seismic attenuation and one simple method that we can apply in order to somehow address the problem of attenuation. Thank you very much and see you soon.